when we're using these special right triangles, we want to learn these in a very, concerted manner, meaning that we want to learn them as fast as we can with a great deal of skill and efficiency, because if I were to lay out the rest of the course for you, with all the problems that exist in the rest of the course, it would blow your mind how many of them have 45, 45, 90 right triangles or 30, 60, 90 right triangles in them, okay? And that happens for several reasons. One, these triangles are present in a lot of extra concepts, okay? So they're foundations of other concepts. But additionally, if I'm an author writing a question, I can give you a 30, 60, 90 triangle in which I give you one value, but ultimately it hides two others to you. I imply essentially three values with giving you just one. Does that make sense? So that's a nice thing for an author to do when writing questions. So they're going to be present beyond this. They're also key to finding areas of a lot of other shapes. Okay, so those are things that we're going to use quite a bit. So getting skilled at setting the relationships up is going to be important, but at the same time, developing the proficiency within the algebra of reducing radicals, multiplying, adding, subtracting, dividing radicals is going to be very, 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 very important. And I've been trying to kind of get you to recognize that, or I've been talking about that for about, probably since about Christmas, that radicals are going to become part of everyday life, okay? That everyday life is here today, okay? So we're going to be using radicals on a consistent basis. Please, if you struggle with them, take the steps to get those struggles resolved. Whether they're asking questions, whether they're doing extra problems, watching the videos, all that kind of stuff. There are tools and resources out there for you to brush up on your algebra skills. Okay, so we're going to do a lot of examples today, but at some point, the simplifying of radicals and all that kind of stuff is just going to be something that, you know, if I see radical 12 up there, I'm going to automatically write it's just 2 radical 3, and you have to be able to follow that and understand that. Okay, or you're going to get lost, because I can't spend the 5 minutes to simplify a radical as a kind of preliminary step for the other things that we do in geometry, because the other steps are going to take a lot of time as well. Okay, so some of that algebra will have to be skipped over a little bit. Canyon, is there a question?
Yeah. Those big ones, is this a right cube or obtuse, so they'll have 2 radicals and then a 6. I didn't know how to.
So you got a right triangle. Do you have, like, so it gave you like a radical? Okay.
Radical 38, radical 2, and 6.
Did it give you the picture or just say? Okay, so radical 38, radical what? Radical 2, and 6. Okay, so here's what I would do. I would put all of these in kind of the same format to first see if, or see which one is the hypotenuse, if this thing's going to be a right triangle, correct? Is 6 the same thing as root 36? Okay, so if I put all those in the same format, now I can just look at the numbers underneath, the radicands, and say, well, radical 38 is the biggest, right? So what this is saying is that radical 2 squared plus radical 36 squared, does that equal radical 38 squared? If that's the case, so here I get radical 2 squared is 2, right? Radical 36 squared is 36. Does that equal radical 38 squared, which is 38? Yep. So that's true. So if it's true, what kind of triangle is it? It's a right triangle. Okay. If it was false, then we would have 38 either less than whatever these numbers were that would have made it false, or we could have 38 greater than whatever these numbers were added together that made it false. If those are false, so if 38 is less than, that would be acute. If 38 is greater than, that would be obtuse. Yes?
Is 8-2 due tomorrow?
8-2, these 8-2 assignments, guys, are not due until March. Okay, but do not wait until tomorrow, because tomorrow we're going to move on with more of this stuff.
Yeah, not that 36 and 90, just 8-2.
Oh, well, I forgot about that one. Yeah, I think I got that set up tomorrow. Yeah. My apologies, yeah. But the Blizzard Bag Day ones, those are due March 1st or something like that. Yes. Okay. Let me get to through today's stuff. If we have time with that question, Jim, and I'll answer that today. But if not, I'm going to open up class time tomorrow, pretty much all class time tomorrow, to ask any questions over these assignments that are open, and we can kind of hash those issues out. But I think going through some stuff today over the videos that I asked you to watch, and again, some of the 45, 90 questions are going to be useful for maybe answering some of those questions. Now, I understand the videos. If you couldn't watch them because of eyeballs, like I did send out an email. I've told you this before. That's the school's filter, right? So some reason when you're at home, YouTube is filtered differently than it is when you're here. My videos, for some reason, get blocked. I don't know why, and pretty much the tech people don't know why either, because they seem to not fix it. They'll fix it for a month, and then it goes back to the way it was. I'm continually trying to get them to fix that, but a workaround for that is to use a device that's not school affiliated. Okay, use a cell phone, use a iPad or some other tablet or some other computer, something like that. If it's available. I know some of you don't have that available. So I do want to talk about some of the stuff that was in those couple videos. The one thing that we did talk about on Tuesday, we wrapped class up on Tuesday with this, is the idea that if I've got this type of triangle, these are both 45, 90 triangles, I'm going to talk about the blue one and the red one. So this blue one here, obviously, if I were to ask the GeoGebra to do this, this is 3 by, nope, sorry. Now there. That's 3 by 3, right? Okay. So that's isosceles, so these angles got to be 45, and 90. Every time that we do this, and it's because of the Pythagorean theorem, and I proved it to you on Tuesday, that your side lengths are all going to be in comparison to one another, those values. Okay, so your two legs are always going to be identical, so they're both maybe some number n. And then your hypotenuse, because of the Pythagorean theorem, is always going to be that number times radical 2. Okay? What's nice about that is that when they give us then a question over here like, so 1, 2, 3, 4, 5, this is both 5 by 5, yeah. They give me that to be 5. Can I use that information with this picture here to come up with the other two missing sides? Okay? And the idea here is that this blue one, I don't know what n is. Does that make sense? So even though it's smaller than my red triangle, the idea is that we're going to expand that, we're going to enlarge it or reduce it so that it matches up 100% with my red triangle. Does that make sense? If I were to match those up, if I was to expand that one or enlarge it so that they match up 100%, it's that segment right there match up to that segment right there. Does that make sense? And if they were the same triangle, those two things would be congruent, correct? So does everybody see that n would be congruent to 5? And if I've got two segments that are congruent, their measurements are what? The same. So does that develop the little equation, n equals 5? Not the trivial equation. It's not a really interesting equation because it's already solved for, right? But now that I know n is 5, can I come up here, okay, that side was in, so they're saying this side is in as well. When I put that blue template on top of this one, doesn't that become 5? And then doesn't my hypotenuse, for the same reason, become 5 radical 2? Does that make sense to everybody? Okay. In the other classes, we've done this. I put my axes in here. Is this point 0, 5? Is this point down here 5, 0? Can I use the distance formula, which says delta x squared plus delta y squared? If I square root that, I should still get 5 radical 2, right? It's a different approach. It's now using coordinates, but change in x would be 5 minus 0, so that'd be 5 squared. Delta y is the change in y, so 5 minus 0 would be 5 squared. Does that give you 25 plus 25? 25 plus 25 the same thing as that? 25 times 2? What's the square root of 25? 5. And if I take square root of 2, it's just that, right? You see I get the same result, the same answer, but a different approach by kind of implanting that thing in the coordinate plane. So hopefully doing that two different ways, using the special right triangle and then using the distance formula, convinces you that what we're doing here with this template is an accurate and appropriate approach. Okay, it does work, and it works every single time. What has been a problem, I think, in the past for people is when they give us, obviously that's my n radical 2, that's n, that's n. When they tell me that this side over here is 14 radical 2. Well, if I overlap those, doesn't 14 radical 2 match up to n radical 2? That make sense to everybody? Now, there's two ways of approaching this. If I want to make the left-hand side and the right-hand side identical, what do I have to replace n with? 14. So does that automatically tell me n is 14? Okay, but that's not really algebraic, right? Let's actually go through the operations that we would go through to isolate n. The first thing I want you guys to understand, and I don't know how much we talked about it in this class because there's a couple classes that we didn't talk about this last week. N radical 2 is equivalent to radical 2 times n. Does that make sense to everybody? For the same reason, if I had like n times 2, is that the same thing as 2 times n? That makes sense? You guys remember last year, maybe the first couple days, you were taking a variable times a rational number, and you could write it this way, but then Ms. Scholes, or whoever your math teacher was, would have told you the general accepted policy is to write the coefficient first, right? When you have rational coefficients. When you have irrational coefficients, a lot of times, especially if they're radicals, we write the coefficient last. And the reason for that is this root 2n, or root 2 times n, if I'm sloppy with my handwriting, I could write it like that. And that is not the same thing as radical 2 times n with the n outside the radical. Does that make sense? So it's easily misunderstood whether that n, when I write it behind the radical, whether it should go underneath the radical or not. Does that make sense, everybody? So to alleviate that, we just write it out in front. And now there's absolutely no question of whether it's underneath or not. Does that make sense to everyone? So if we understand that concept, if we understand that this statement right here is true, radical 2 up here in blue, it's just a coefficient. So if I have a variable with a coefficient of radical 2, what do I need to divide by to get that variable all by itself? Radical 2. Divide by radical 2 there. Come over here. Divide by radical 2. Now, this is why it's kind of a one-to-one correspondence or a trivial type of process here. It's because those are going to cancel, right? Gives me n. Don't those cancel? Gives me 14 right away. And because those cancel on both sides that way, that's why it was really easy for us to say, looking at it this way, that n had to be 14. But the algebra of y is this here. We have to divide both sides by that coefficient. Is that okay? Now, why do I talk about that? It's because what happens when they give me a number like 8 here? Okay? You don't see, when I match those two things up, when I merge those two triangles, and I get the equation n radical 2 equals 8, we don't see the radical 2 that is being multiplied inside to make that 8. Does that make sense? Likewise, when I see 8 up there, I don't visually see 2 times 4, do I? It's written as a different symbol. It's written as 8. So that radical 2 is inside that 8. It's just being multiplied by some other factor that makes it a total of 8, or a product of 8. So in regards to doing this, I don't have a one-to-one correspondence. I can't say, well, it's just a number out front or something like that. Here I have to go through the algebra. So how do I isolate n? How do I get that coefficient there of radical 2 to become 1? Divide by radical 2. Do that to both sides, right? So we're going to cancel. It gives me n is equal to 8 over radical 2. Now, that is my exact answer, but it's not a sufficient or usually acceptable answer because we don't like radicals in the bottom. Okay? Remember how I can get rid of those radicals? Multiply. What number can I always multiply a number by so that I don't change its amount? 1. It's the multiplicative identity, right? That's what we called it last year. Okay? Radical 2 over radical 2 is a fancy version of 1. So I'm not going to change what this amount is. I'm just going to change the way it looks. Here's my next question. How do I multiply radicals? I'm going to multiply straight across here. What do I get? 8 radical 2. What do I get on the bottom? 2. Okay. So now that 8 radical 2 over 2 could have come from two different products of fractions. It could have come from something like this, 8 over 2 times radical 2 over 1. If I multiplied those two fractions together, would you agree that they give me that red 8 radical 2 over 2? Okay. Or they could have came from this, 8 over 1 times radical 2 over 2. Would you agree if I multiplied those black ones together, I get this red expression? Okay, one of those is useful, one of those is not useful. And the reason the black one is not useful, what's radical 2? Does anybody know what that approximates to? 1.4-ish. Okay, it's like 1.414, right? If I approximate it, it's an irrational number, so it goes on forever, never ends, never terminates, never repeats, anything like that. But does 1.414 and 2, do they have a common factor within one another? Like a whole number factor that would cancel out? No. 1, that's it, right? But they don't. So this black one, for that reason, is not really great to look at. The blue one is nice to look at, because if I look at radical 2, which is a 1.414 over 1, well, that's just radical 2, right? Okay? The nice thing about looking at this blue one is that 8 and 2, do they have a common factor? Yeah, 4, right? Or 2 is a common factor, and they cancel out to give me 4. So this red one here is actually going to simplify to 4 root 2. Okay? Now, a lot of you might have already known that, or so that's a big explanation for just knowing that I divide the 8 by the 2, right? I divide the number that's on the outside by the number that's in the denominator, and that's fine. That works every time. What I don't want you to do is make sure that you understand why I cannot take that radical 2 and divide it by the 2 as well. Because I get a lot of people say my answer here is 4. And what they do is they say 8 radical 2 over 2. So the 8 divided by 2 gives me 4. They say radical 2 divided by 2. Well, I take the 2 and divide by 2, I get 1, so I get radical 1. What's radical 1? It's 1, so they say I got 4 times 1. That's erroneous. That doesn't make sense. Okay? You can only divide the number that's out in front of the radical by your denominator. Does that make sense, everybody? And it's because of how we multiply fractions and how we look at common factors. Is that something we can do? Les, is that something we can do? Sure? Guys, we're gonna have to do this on a regular basis. So if there are questions, make sure those questions get asked. Just generally speaking, if I'm multiplying radicals that look like this, where A, B, C, and D are just numbers, just integers, okay? Does anybody remember how to do that from last year? What things am I going to multiply together and where do they go? Okay, I'll take A and C and multiply them together. And because they started on the outside of their individual radical expressions, they're going to start on the outside or stay on the outside in the product. And then what goes on the inside here? B and D. Okay? Now think about what happens here. If I have 2 radical 3 times 4 radical 6, I'm going to get 2 times 4, which is 8. I'm going to get 3 times 6, which is 18, right? Now think about this. 3 and 6. They have a common factor, right? What's the common factor between them? 3. So when those common factors of 3 get multiplied together, they develop a perfect square, don't they? So when I take 3 and 6 and multiply them together to get 18, I have now created a radical that is not simplified. And that perfect square that's going to be in here is 9. Does that make sense, everybody? So I'm going to take 8. The 9 turns into, so I have radical 9, radical 2, right? So that radical 9 turns into a 3, and I got my radical 2. So this turns into 24 radical 2. Okay? Every time that you multiply two radicals, make sure that when you look at your final radicand, the number underneath the radical symbol, make sure that there are no perfect squares inside it. If there are, continue to reduce until there are not. Okay? How can I check that? How can I make sure that this is correct? Can I take my calculator, type that in right there? Get a decimal? What should that decimal be in comparison to the one I just found then? They should be the same, right? And those types of things, being able to take your calculator and taking one format of a number and see what its decimal looks like, and then taking a second format that you think is right and seeing what its decimal is, can provide you insight on whether your algebra rules are being conducted correctly or not. Okay? A lot of times people ask, can I do this? Well, plug in your calculator one way. Go through the route that you think you can do, see what that algebra would provide you, what result you would get, and then plug that in your calculator. Are the two numbers the same? Then that answers your question. Yes, you can do it that way. If your answers are different, then that answers your question. No, you can't do it that way. Okay? So that's dealing with 45, 45, 90 right triangles. So hopefully, just predominantly speaking through my career, I've noticed that people usually do okay with those triangles. It's these next ones that are the big issue, and they're 30, 60, 90 triangles. Okay, so I want to draw a equilateral triangle here. Try to get it set up. There we go. All right, that's an equilateral triangle. We have learned in Chapter 4 that from point A to line BC, or segment BC, there is one line that will be perpendicular, right? Okay. If this was equilateral, what are all three of these angles, B, C, and A? 60 degrees. Does anybody remember if that's 60 degrees, what that black line does to that 60 degrees? Cuts it in half, so that's 30 degrees. So did that just generate a 30, 60, 90 triangle here on the right-hand side? You got one. You got the reflection over here on the left as well. I'm going to deal with this one on the right-hand side. Basically what happens, guys, is that because of this equilateral triangle getting intersected by this altitude, or creating this 30, 60, 90 with this altitude, we get a relationship between all three side lengths of this triangle on the right that are very, very, very convenient. Okay? Now, you can choose any number you want. You can let my hypotenuse be 3, and you can go through this process and figure out the relationship between that number, the number across from the angle that's 30 degrees, and the number that's across from 60. You can let it be 31, and you can do the same thing. You can let it 310, do the same thing. The best thing to do is to let this be 2. Okay? And really what I'm going to do is so that I can say that it's really any of those numbers like 3 or 310 or whatever, I'm going to let it be 2 times n. Because now if I want it to be 3, n just has to be 1.5, right? Does that make sense? Okay? So that side length is 2n. So what's that tell me A to B is? Yeah, this side here, 2n. What about this side? 2n. Okay? Now, back to, so that was an equilateral triangle. Equilateral triangles are also isosceles triangles, correct? Back to Chapter 4, we talked about when we draw the altitude in an isosceles triangle from the vertex angle. So angle A would be a vertex angle here. Perpendicular to the base. Does anybody remember what it does to the base? It bisects it. So there were two properties there. It bisects the vertex angle, and it bisects the base. So that distance there is the same thing as that distance there. Okay, so that's nice because what does this thing right here become then? That becomes n. Half of 2n, right? Do you see now in this right triangle that you now have two side lengths that are predicated or based off of the exact same value n? Okay. Well, it'd be really nice if I could get that purple segment to be based off of n as well. And we should, because what kind of triangle is that triangle on the right? It's a right triangle. What theorem always exists with right triangles? Pythagorean theorem. I'll call that B. And that's what I called it in the video I asked you to watch yesterday. But if I take B, which is a leg, I should be able to square it, right? Add to it the other leg. What would be the other leg in this 30, 60, 90 triangle? N, and square it. And that should equal my hypotenuse, 2n, and I'd square that, right? Okay, so the left-hand side looks like that. The right-hand side, what's 2n squared? 4n squared, right? B squared is then going to equal 4n squared minus 1n squared. What's that give me? Say again? 3n squared, good. Now can I square root both sides? Okay, so I square root that. Square root that. So give me B equals root 3 times root n squared, right? And what's the root of n squared? N. So B, which is this vertical distance here, now just became n radical 3. So are all three sides of that 30, 60, 90 triangle then based off of whatever n is? Does that make sense to everybody? Okay. So I'm going to draw. Now I'm going to ask you to prove that at some point, maybe in a higher level math class, maybe college algebra, trigonometry. My trig students, we did this a couple weeks ago because 30, 60, 90 triangles are extremely critical for trigonometry. Without them, we don't have a lot of stuff that we do in trig. Let's see here. If we have a 30, 60, 90 triangle, so this angle here was 30, this was 60, that was 90. This is all in our template. That's always 2n, that's always n, and that's always n radical 3, right? Okay. I want you to tell me which one of those is the biggest. 2n, always. I want you to tell me which one's the smallest. Okay? Because if n was 1, this would be 1, and this would be radical 3, right? Radical 3 is approximately 1.7. So this one's a little bit bigger. Does it make sense matched up on the angles that across from 30 is always the smallest side? Across from 90 is always the biggest, and across from 60 is always your middle one, right? Okay? The reason I say that is because when I draw, what is this, 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6, 7, 4 by 7. When I draw that triangle, and I put 90 there, what is the hypotenuse going to be? 2n. This is now the 60-degree angle, and this is now the 30-degree angle. What should E to F be called? That's going to be n, and that's going to be n root 3. You see how they change? Okay, the side across from 60 always gets stuck with n radical 3. The side across from 30 always gets stuck with n. Okay? With your 45, 45, 90, that wasn't an issue we had to talk about because the legs are both the same, right? But here, because they vary, you have to be cautious. You have to pay attention. Okay? All right, so let's do a couple examples of 30, 60, 90s. The process for generating these problems and the questions that exist here is exactly the same for 45, 45, 90s. So let's just say I'm going to take that one to the side. That's going to be my template. So that one has always got, on the hypotenuse, that's always 2n. Let's say that this is 30 degrees up there. So this would be n down here, and this would be n root 3, right? Okay with everybody? So now if I told you over here that this is 30 degrees, this is 90, and told you this was 6. Can you, if it's a right triangle, Can you tell me the other two parts? What are they? Jimmy?
A to B is 633.
Good.
And A to B is 12.
Good. So when I overlap these, n landed on 6, right? So then everything else is predicated off of n. Hypotenuse is twice that, so it's 12. Side across from 60 is n radical 3. Pythagorean theorem should satisfy this, right? Or these should satisfy the Pythagorean theorem. Maybe saying it that way is better. 6 radical 3 squared plus 6 squared should equal 12 squared. What's 6 squared? 36. What's radical 3 squared? 3. 6 squared is 36. 12 squared is 144. That's 36 times 4, because that's what that's going to be, right? Does 36 times 4 give you 144? Yes, it does. Okay. But what's nice about it, so that's using the Pythagorean theorem. What's nice about this is that if I wanted to use the Pythagorean theorem at the onset of this problem, can I? Can I use a squared plus b squared equals c squared to find the hypotenuse here or anything? How many things do you need equals c squared, or to use a squared plus b squared equals c squared? You need 2, right? How many am I giving you right there? 1. So without the special right triangle concept, there's no way of finding those parts of that triangle. Okay? So that's what these special right, they call them special right triangles, but it's essentially just the Pythagorean theorem. But it allows us to use the Pythagorean theorem when I only know one value of those specific triangles. Okay? Yes?
Does every right triangle have something sort of similar to that, and they're just
but these are more common. I mean, you could probably develop some other relationships but they're just going to be just like pretty random. But 30, 60, 90, and 45, 45, they occur naturally a lot. We use them in construction a lot, so those are the ones that we use predominantly. Okay, guys, so let's do this. Let's say that I gave you this side to be 18. So what would be the little equation that I develop when I put this small one on top of the big one? Good. So then n would be 9. So that's across from what angle? 30. So that's 9. So now what would be across from my 60? 9 radical 3. 9 square root of 3. Is that something we can do? Okay. What if I give you this? What if I tell you this is 5 radical 3? What's the little equation you get there? Okay, so what's n going to be? 5, and that goes across from what angle? 30. And what's going to be my hypotenuse? Careful. 10. Okay. Now, usually what is hard is this type of stuff. What if I gave you this to be 10? 10 equals n root 3, so now what do I have to do? Divide by root 3, divide by root 3. So we get 10 over root 3. What am I going to do with that? Okay, so we get 10 root 3 over 3. That's my n value, right? Does that simple? Does the 10 and the 3 right here, do they cancel out or anything? No, they're relatively prime to one another. So that's n. What side does that go across? 30. So I get 10 root 3 over 3. All right, now what do I do with that number to get my hypotenuse? Times it by 2. So here's the thing. When I times it by 2, I've got fractions, right? How do I multiply fractions? Straight across, okay? Now when I multiply these straight across, the denominator is going to be 3, right? How do I multiply the top? Okay, it becomes 20 root 3. Now the reason for that, what can I multiply 2 by so that it's a what radical can I multiply 2 by so that I don't change the quantity of 2? Okay, not just because 1's not a radical. Radical 1. Okay, because radical 1 is a convenient value of 1, right? And simplifies to 1. So it's not going to change the 2. The reason I would do that is to explain the idea of how did I know to multiply the 10 by 2 and not this 3, right? The reason for that is because our rule that says you multiply the numbers that are on the outside, so the 10 and the 2, and they stay on the outside. Then you multiply the numbers on the inside, and they stay on the inside, right? Now, when I get that, do any of those numbers on the outside reduce? Does 20 and 3 have common factors? No. So now I have 20 root 3 over 3. And that's my hypotenuse. Is that all right? Okay. Now, we got a little bit of time here, so I want to talk about the one that Jimin was mentioning at the beginning class. You have do you know what question number it was, Jimin? 11. And that's on the 30, 60, 90 assignment, right?
Hey, why didn't we apply
So you get something like this, and they put a right angle down here, and they put a right angle up here. I think they tell you something to the effect like this is maybe 11. Actually, I think the picture's upside down. I got the picture up there on the board already. Let's do it this way. So something like that. So they give you this top here to be something like 11. They ask you, or they tell you if this is like 7 radical 3. They put an angle measurement there. Now, it could be 30, could be 60, could be 45 as well. And then they tell you they're wanting to know what B is down here. Okay? Well, the way we go about doing this, guys, is that when you see this figure, the fact that this is a right angle and that's a right angle tells you what about the top line and the bottom line? They're parallel. So that should tell me that I'm able to take this segment D to A, and I should be able to move it to maybe there, and it'd be the same length, right? Now, the best place to move that DA in this picture is right there. Because when I put that 7 radical 3 there, and I move that, so this, when I move that, that's parallel to that, right? So doesn't that have to be a 90-degree angle there? So what kind of triangle is this on the inside here? 30, 60, 90 right triangle, correct? Across from 60, in my template, that is always n radical 3. Does that make sense? So what is n in this case? N is 7. What side is that going to go across? Okay, so over here is 7. My hypotenuse would be, I don't think they ask you, but what would that distance be? 14. Now, how do I find B then? 11 minus 7. So it gives me 4, right? Obviously, I didn't draw it to scale, and it's probably not going to be to scale when you do it on your problem math Excel. But that's kind of the approach there. Somehow you should be able to segment your pictures up to where you get 30, 60, 90, or 45, 45, 90 triangles. And that's what happens a lot later on. When we deal with, just kind of giving you a heads up on this, one of the harder things that we're going to do later on is area. And we're going to talk about area of these types of figures, areas of the hexagon, okay? Now, the reason we talk about the area of the hexagon a lot is because if we were to look at these triangles in there, okay, this triangle right here, anybody know what kind of triangle that is? It's equilateral. So if I do this, what is this little triangle right here? It's a 30, 60, 90, okay? And that 30, 60, 90, if they give me one distance on that, should tell me how to find the other 3 distances, which then tells me how to find the area of that little triangle. Does that make sense? If I multiply that little triangle's area by 12, I get the area of that regular polygon, okay? Or that hexagon in this case. So that's kind of where this stuff is going to lead us to, and other applications of area, volume. We do some probability with this stuff as well. There's some questions that pop up with probability of these types of triangles. So it's something that's going to be very, very, very important for us to get a grasp of. And a byproduct of that is the algebra, okay? The working with radical, simplifying, all that kind of stuff is going to be essential. I sent out